Okay, I guess we're already starting 5 minutes late. It's the longest session of the summit. So, and we have 5 speakers, so the last session for today is quite packed. So first, we have José, who is nearly as long with the RIOT community as I am. And for the past 5 years, he worked a lot on our 802.15.4 layer. So, yeah, have fun with this talk.
Thank you so much. So I would like to start with the motivation of this talk. This is how the legacy 15.4 architecture looked like back then, 2015 to 2019. What we see here is that sub-network stacks such as GRC and Lightweight IP, which expect a MAC-like interface, so that means they send and receive link layer data mostly. They were connected directly to device drivers using the NetDev interface. And at some point, we start adding other network stacks such as OpenThread and OpenWSN. And these network stacks require a different interface. They were mostly communicated using file-like interfaces. And what we did back then, we start connecting these network stacks also with the same NetDev interface to the device driver. But here we're seeing we are actually having a NetDev interface that exposes MAC-like features and file-like features. We see this mixes MAC and file concepts. Also, all MAC features were dependent on the device driver. The same thing for file features, which come to these 2 problems. First problem is this fact that the NetDev implementations were delayed between file and MAC leads to conflict in network stack and makes it really easy to control the transceivers at a low level. For example, if we want to transmit a frame with a transceiver, the operation is usually loading a frame, then transmitting a frame. But since we have a mixed PHY and MAC layer in NetDev, we will need to first set a need or preloading function, then send a frame, but it's actually not being sent, it's actually being kept on the frame buffer. Then we will need to trigger TX start, and then we will need to set the state to idle back. So this makes it quite tricky. On the other hand, since we don't have unified MAC layers, each transceiver handles its own MAC features, and therefore this leads to inconsistent behavior of CSMA-CA transmission. I put this figure there. Most people prefer back then the Atmel radio or the MRF 24J40 because they implemented CSMA with retransmission, whereas the poor Nordic radios, kinetic radios didn't do that, and they yield worse performance. So the remaining of this talk, I will talk about the components necessary to go to this uniform 15.4 integration, namely the Radio HAL and the SubMAC. Also, I will show a little bit how this process went, what were the lessons learned, and some potential next steps for the RIOT community on this regard. So our goal is twofold. On the one hand, we would like to have a unified SubMAC layer. What's a SubMAC? Basically, it accounts for CSMA-CA and retransmission. So this doesn't include commissioning, joining, and other stuff that are included in the full 15.4 MAC. But if we would like to do that at some point, we can just implement it on top of the SubMAC. So the idea is that this would work for all kinds of transceivers. And the counterpart would be the 15.4 Radio HAL, which acts as a direct hardware access HAL with optional hardware acceleration. If a device supports some kind of hardware acceleration, then of course we would like to exploit that. So the 15.4 Radio HAL in a nutshell, this is a modular API which mirrors the logical device functionalities. For example, we know a device can be turned on and turned off, so we have an API module for power management. It has a frame buffer, so we can read, write, and get the length of the received packet. And 2 important API modules we have here are the operational controls, where we can indicate to the transceiver, okay, please go to reception, please trigger a transmission or perform CCA. And since we have different hardware accelerations and different properties, we need a way to do capability reporting, as this is what we call the CAPS. The idea is that upper layer can query the device to see whether the device supports auto CSMA-CA, whether it supports a TX down event. And with this information, of course, the upper layers can react accordingly. Also, we wanted to do this non-blocking because it makes easier integration with most network stacks. The problem is not all drivers really have all kinds of events. For instance, the CC2420 does not have a TX down IRQ line, and we need a TX down event for TDMA stacks such as TISH. Therefore, we came up with this pattern, which I will show in the next slide, which is this request confirm operation mode. The idea is that an upper layer, could be a MAC layer or direct user, could request an operation. In this case, you request a transmission, for instance. If it was okay, it returns okay, then the device driver, or the device in this case, will start doing something, in this case, transmitting the frame. And the upper layer must confirm this operation to flag that this is already finished. So if we try to confirm this operation while it is transmitting a frame, the API will return busy. At some point, the device will finish doing whatever it has to do. And at this point, if the upper layer calls a confirmation, then it would get the OK status, which signals that the radio finished doing something. We can also fetch the status of this operation. In this case, corresponds to a CSM ACA with retransmission hardware. So we get, for instance, that the transmission was successful and it required 2 retransmissions. In case a device doesn't have an event such as the TX known event, we just need to fall back to Paul. How do we know that we have to do that? Just by using the radio caps. So we got some early insights of this. We could port this to OpenWSN and later to OpenDSME, and we could validate basically the API by seeing that it's cross-stack compatible. We also realized that since we are only implementing the minimal stuff required for the devices, most Radio HAL versions actually have a lower footprint in terms of ROM and RAM than the NetDev variants because the implementations are really slim. And also, since we have full control of the radio, we can achieve low power operation. In the case of OpenDSME, we could achieve 330 microwatts and 100 microwatts for sleepy-end devices with indirect transmissions, which doesn't sound that low, but these are online devices. So these are devices that can be reached. So basically, on both directions, they can send data, but they can also receive data with some latency. Then the second component is the SubMAC. As I mentioned before, this allows for reliable communication by using CSM ACA with retransmission, regardless of this is done on software or on hardware if it's available on the device. And we follow a capability-driven finite state machine. The idea with this is that, for example, if a device does not perform automatic retransmissions, then we would need to go to a wait for acknowledgement package state, where basically we would handle this state. And in case the radio can handle most of this stuff alone, then it would visit probably only 2 or 3 states. So basically it adapts depending on how the radio capabilities are. In order to make this work on the existing infrastructure back then, we implemented a NetDev interface on top of the SubMAC. So this creates a NetDev device that has full support for CSM ACA with retransmission. And we thought about this initially as a migration layer, but in the end, it escalated and it kind of became permanent. Wait for us in the lesson learned section, which I will talk a little bit more about this migration strategy. So this picture shows a little bit the timeline of the process. As we can see here, this process was quite involved. It was really hard to come with a final version. Just to put you some context, we started thinking that we could do this rework on the IETF 104. This was, I think, the 3rd attempt to get OpenWSN into the RIOT network stack. And we realized we had to do something. So we used the Corona times there in 2020 to start with the proposal. And we started adding devices, doing proof of concept PRs, iterating, changing stuff, adding new stacks, removing stuff. And around September, we got to a state where we could first test the first variants. But if we see here, we actually got it merged in the final proposal, this Radio HAL RDM, on April 2023. So 3 years later after we presented this concept. So this shows that it was quite long, quite involved. It involved at least 13 RIOT maintainers and developers. So yeah, it was hard, but we're really happy that after we merged this, we have seen at least one new radio that was not considered at the moment we designed this API, which is this ASP32H2, which got recently merged. And yeah, this proves that this is kind of working. And here I would like to go with the lessons learned throughout this process. The same lessons is that it's very important to choose the trade-off wisely. We spent so much time trying to find a perfect interface that would work perfectly for all kinds of devices. In many cases, we probably got 80% of devices working right. And we just dropped this because we thought, okay, this 20% of devices couldn't do that in this way. In the end, it didn't matter. Actually, many of these trade-offs, we could have been setting them earlier if we just tailored some, create some tailored proof of concepts, and we would have saved so many months. I think it's very important to know that there's really not such thing as a perfect interface, and sometimes it's fun to find this sweet spot. The second lesson learned is to be very careful with the migration strategy. So we created this network 15.4 SubMAC just as a way to be using the same interface or the same network stack as we were using. So basically try to do everything in parallel, but of course this has overhead. And at some point it became permanent. But at this time, if we would like to remove this, this component, it would be really hard. In my opinion, and also talking to other RIOT maintainers, probably in this specific case, it would have been better to just do a clean break like the I2C embargo. Would have been definitely easier to manage. And we compare also with the case of kconfig, and we think that one of the reasons why the migration failed was because we struggle a lot having parallel configuration systems. The third lesson is no docs means no memory. It's very hard to try and changes and design decisions over time. As you could see on the timeline, this was basically 3 years of work. And at some point you start forgetting why we did the stuff the way we did. In that regard, the RDM, this RIOT developer memo, helped preserve the discussion and guide it for some time. But for instance, there used to be an early Radio HAL in 2014. Apparently it was forgotten, no one flagged it during the rework, but it existed back then. It looks kind of different to what it looks today as a Radio HAL, but it could have probably saved us a lot of time. So to finish this presentation, I would like to introduce you to two proposals. This is myself, by the way, 3 years ago for the RIOT Summit 2022, where I did this work of IEEE DSME MAC over LoRa. And on this work, I reused the Radio HAL for writing a LoRa, basically a LoRa driver. And I realized that basically most transceivers do the same kind of operations. They load data on the frame buffer, they send something. So basically, why don't we extend this concept of a 15.4 HAL to other kind of transceivers? In the case of LoRaWAN, this would be really beneficial because LoRaWAN stacks require direct access to the devices. Also, since the API is minimal, it's reduced implementation complexity. And since we have a smaller surface, it's easier testing and gives us less back. And the second proposal, which is probably rethink the concept of how we use NetDev. As we have it now, it's mostly a way to abstract network stack with device drivers. But probably we should think of how to do it in a way where we could use it as a stack-independent way to send link layer data. We have SOC UDP for sending UDP data regardless of the stack, same thing for SOC IP, but we currently don't have a way to actually send link layer data without being dependent on the stack. If we do something like this, then we could actually have, for instance, a generative that would be only a very thin wrapper over NetDev. I would like to leave this probably for discussion offline later and in the coffee break, but it's something we could definitely think about it. So that's my presentation. Thank you so much for your question. Of course, I'm open for questions.
Any questions? Yeah. Some kind of tests to verify that the interface. And I was working something like that, but I had this issue that I didn't really know if the implementation was actually inferior to the API's truth because it's a state issue. Is there some way to test this?
Yeah, actually, this idea has been there for at least 2 or 3 years. Back then, there was a student that tried to do something like this, but he didn't finish such a test. But that's the idea. In theory, it would be possible to test whether Radio HAL implementations comply with the abstract state machine. And that would be definitely desirable. We could think of hardware in the loop testing for this kind of devices. Most operations are about testing, for instance, timing between going from Rx to TX. So we could definitely do that. It would really benefit the lower layer infrastructure. It just has to be done.
More questions? Okay, thank you for saying.
Thank you.